So please, if you have complex questions, please, you can let me know. I will direct them to him. Okay, so this talk is based on, it's a benchmark analysis that is done for explainability in terms of a deep learning method for morphological classification of radio galaxy. So just to give a bit of background, so there have been previous work using deep neural network in terms of classification of radio galaxies. I have highlighted here one of those work, which was done by Arun Anand, where he developed an algorithm for classification of galaxies with different type of FR1, FR2, and so on. And he also found that deep neural network, despite being fully automated, can give us reliable results. I mean, the classification was good enough with a good F1 score. However, there are still issues such as if you use a deep neural network, so they are heavily dependent on the sample size. So if we don't have enough of data, so the result is not going to be that accurate. And the second one is unbalanced data set. That is, if we have some type of galaxies, the percentage is less with respect to other set of galaxies, then we might introduce bias into our result. And the third one is lack of understanding on the decision-making process. As we all know that when we use any type of deep learning network or machine learning, it's like a black box. So we don't really understand, there's a magic that goes on, but we don't understand what's happening. So this talk will focus on the lack of understanding by using a method called explainability. So in terms of explainability, it can be categorized into two sets. The first one is we can use explainability to give explanations that give insight into model training and generalization. And the second one is to give explanations that give insight into model prediction. And I'm going to focus on the second one, which is explanation that give insight into model prediction. And for that, there's briefly, literature has classified into three different methods that can be used to give insight into model prediction. And the first one is visualization method. That is, we could illustrate those pixels that influences our decision or the decisions that the network makes, and highlighting the different characteristics of our input. The second one is model distillation. So model distillation tries to, so when we give an input, it doesn't use a whole input, but tries to break it into chunks, which translate it from being a black box into a white box, which is more easily interpretable to understand the decision-making process. And the third one is intrinsic method, whereby the design of the network is designed in such a way that it already have the information along with the output. For instance, we have linear model and we also have decision tree. Now here we're going to focus on visualization method. So when we talk about visualization method, so there's an attribution factor that is given to each pixel in our image or to the input. And it is a degree of association to which a network considers the input feature to the decision making or the input importance it gives to the decision making. And we use saliency map, or also called heat maps, for that, whereby we can identify the input features that are salient features. And here we're going to focus on the backpropagation based method. I'm just here's just a generalized, here's a generalized generalized explanation of the network, where you give an input, you have the hidden layers, and then we have our output. But I will just break it down into a simple network here, which shows how we are going to integrate our saliency method here. So here, if we just take an input image. So we have several input image, which is represented by DN here, DM, which is M is the number of images that we have. And XI is a single image as input. So when we give this input here, it goes to our neural network, which is a CCN network in this case we use. And it uses an operator, and it undergoes all the model training and so on. And then gives us our output, which is the Z here, which is a probability. And once we get the probability, we now feed it into the attribution process, whereby we use an attribution operator, which gives us the saliency map or heat map, which is highlighted here. And this heat map, there's several ways to actually generate those ones. So here we focus on the gradient-based method, which uses a derivative of the probability Z with respect to the input. And what it means that if you have a large gradient at a pixel, it suggests that the feature is significantly influenced under the model decision. In contrast to when we have a small gradient at a pixel, it suggests a feature that is fully influenced by the model decision. In this work, we tried 10 method gradient-based method. In summary, I won't go into detail, but we could classify them into like 4 basic means. The first one is where you just use a pixel gradient with the input image itself. And the second one is integrated, which is a blur. You would see this highlighted in purple in here. This is an integrated gradient, whereby we use a baseline path, which is the input image to the output, because we calculate the gradient based on the baseline path. And the third one is the grad cam, whereby we use the neighborhood. It's a region based. We don't calculate the gradient based only on the focus pixel, but instead use a neighborhood region. And if you have smooth and so on, it's just trying to apply a filter to them. So it's just upgraded version of those ones. And we have score cam. Score cam is actually not using the gradient, but instead using the score, means the confidence level on each pixel, to calculate how the decision-making process was done. So to do that, we used a data set, a Mira-based data set, which contained 1,256 radio loud AGN. And this is a survey from NBSS and FIRST. And they were filtered to 0.05, between redshift 0.03 to 0.1. And you can see here on this table. This is I've taken from the paper where they represented the data set. So it's classified into 4 types of galaxies, which is FR1 and FR2, which is basically defined by the region from the center of AGN. If the galaxy is located less than half angular size, it's classified as FR1, or else it is classified as FR2 galaxy. And the other things that the data set provides us is a confidence, which is 0 and 1. If they are confident with a classification, it's 0. If they are not, it's 1. And the digit free is a different morphology of the galaxies, which have standard double wide angle tail, diffuse, and also head tail. And for this work, we considered a subset of 770 radio galaxies. It is this number because we chose only the FR1 and FR1 and FR2, and those one which were confidently classified. We use those one, and the rest we discarded them, and that leaves us with 770. And that is in total it's 339 FR1 and 431 FR2 galaxies, which is a percentage is highlighted here, 43 and 56%. And the images were of size 150 by 150 pixels. Here I'm just showing an example of how the input images look like. There's few different morphology. You can see we have a double galaxy, as well as we have some diffuse emission as well. And we also experimented on different architectures. So I'm not going to go into detail in that, but we found that by doing experiment, we found that exception, the architecture of exception, provided the good F1 score with only 4 FO1 image, which was misclassified, as compared to the least one, which is a VG G19 model, which actually classified all the FO1 images to be of FO2. And in terms of results, this is what we got by using all this. This is an example of the heat map obtained from the 10 state-of-art method that we use, like vanilla, smoke gradient, force X-ray, and so on. And from this result, we can see that the best ones that highlighted the morphology, I mean, from which pixel is influencing the decision. It's the GradCam++, and the ScoreCam. But out of this three, we could see that the best score is from the ScoreCam, and it gives us, and the reason why it gives us the best result is because it uses a confidence level instead of the region. But even though even a ScoreCam and GradCam and GradCam Plus gives us a good result because they use all the region surrounding the pixel instead of just using the pixel wide, which the other method use. And we get the same thing with a FO2 result as well. It's the same. We found that the best result come from the ScoreCam. Looking at this result, we can say that it's very important to know, and this method is providing us a good explanation of the decision-making process. And when we are classifying radio galaxies, it is very important. And just to conclude, so like I said, it's very imperative because we know that with telescopes that are coming, such as SK, and we already have operating MIACA, which is giving us a lot of data in orders of petabyte. So manually inspecting or classifying galaxies would be hard. It's very tedious. So we'll need some kind of automated system, which for that we'll need to be able to trust our results scientifically, because all the images we have of course radio galaxies, but they are correlated with noise and artifact. So if we are going to trust our result, we need to understand how much we need to trust and if our results are robust enough, because sometimes we might get artifacts that are classified as radio galaxies, and that might be due to various reasons, might be, when we calibrate, we have incomplete sky model and so on. So it's very important and crucial so that we can understand our results. So it's important to integrate a way to explain our results. So we need to integrate an attribution operator. And from that, we found for radio galaxies, the three methods that are good enough or provide us good result are the ScoreCam, GradCam, and GradCam Plus as compared to the other method. And they, of course, they highlight the brightest region of the galaxies corresponding to astrophysical features. And in terms of work, that our next step is to expand, because right now we are using only two types of galaxy, which is FR1 and FR2. But the sample had also other hybrid galaxies, which had on one side FR1 and FR2. And of course, we have other sets of data as well, surveys, which have classified radio galaxies. So we are going to include larger samples so that we can have a better understanding of the attribution process. And lastly, the thresholding method that we are using right now to calculate the saliency or explainability, we use one threshold, which is based on the whole input set, but which is still not very accurate. So moving forward, we are planning to do the thresholding based on this every input. So every input will have a thresholding through which we are going to then iterate. It will go through the feedback loop of the neural network. With that, I will end my talk. Thank you.
Thank you, Sunita. We have time for some questions. So I have one. So this is basically given a neural network trained to do classification to see what it has learned, figure out what the neural network is looking at, as it were. Did you also already go back to literature and apply these leniency maps to the various neural networks that have been trained to do classification, for example, like in DenseNet?
No, we haven't yet done it. Your question is whether we have applied like different neural networks such as DenseNet and so on.
Yeah, so different people have tried different neural networks to for Kelsey classification.
Yes, yes.
Past, and this is basically an analysis showing what the neural network that you use for classification is focusing on. So would that also be helpful to basically see what is the best approach in terms of neural networks for classification to do classification?
Yes, I think because here we are just we are not focused on how well the classification is working. We are focused in how we explain the decision making process. And here it's just we're just starting, and of course we are going to expand it and try to, because other people here we're just basing on one like set of classification method that people have used. But of course we'll expand it and use other. People has already done a lot of classification in this field. So we're going to expand it and apply the attribution matrix to those ones as well and see if it's giving us a good result or not, being successful or not. Yeah.
Okay, thank you. Any other questions? If not, then let's thank Sunita again. And let's move on to our next speaker, Daniel Mitchell from Silo, who is going to talk us through YandaSoft for distributed calibration imaging.
Hello, yeah. So I'm going to give an overview of the distributed calibration and imaging that we've set up for ASCAP. And I'll start by acknowledging the Gadigal people as the traditional owners of the land that we're meeting on. And I'll also acknowledge the Wajiri Amity as I'll show some ASCAP images. Right, so just a quick overview. I'll give a very quick overview of what YandaSoft is. And then I'll discuss a bit how it's processed, give some examples, and I'll also show some recent processing changes that we've been working on. Right, so YandaSoft is a set of highly distributed calibration and imaging libraries and tasks, right? And it's built for ASCAP, but it's certainly not specific to ASCAP. You can use it for general purpose radio astronomy processing. And so So basically, we've got a pretty continuous data rate coming in to the policy center from ASCAP, and we've got 36 beams coming from 36 antennas. So there's constant rate, and we just have to process the data fast enough so that we don't fall behind and have a big overhead of files and observations building up, right? So we've got a few hundred nodes reservation on the Photonic supercomputer, and then we just need to distribute our processing over that so we can process it efficiently. Right, so there's sort of three different types of ways that we distribute it. So the most extreme and important, I guess, parallelism that we use is really the workflow parallelism, right? So we have a lot of separate processes all being orchestrated via Slurm. And that can be, so SBID here is observation. So we can have multiple observations being processed at the same time. In each observation, we've got 36 beams, and a lot of the processing happens separately per beam. And then within that processing, we've got a lot of tasks. There are multiple different imaging tasks and calibration tasks. And they might be interrelated, but they often have different input and output. So all of those can be treated as different Slurm scripts and handled by the cluster itself. And then in these tasks, a lot of the data sets being processed are quite large, and so you kind of need extra distribution of the processing in those tasks. And the main way that we do that in Yandesoft is using MPI, and we distribute mainly across frequency. I've also mentioned here Taylor terms. So you can think of Taylor terms as sort of like a spectral moment or derivative images, where we parameterize the change in flux with frequency for a given pixel, just using sort of polynomial expansion, effectively. And we also have some multi-threading. So just to sort of show that in a picture. So this is an ASCAP mosaic. So going into this, there are 36 beams, several hours of data. But we don't just chuck all the data in and make a single image. We've got, here are 4 of 36 beams, and for each of these, you've got lots of different things happening. You've got bandpass calibration, self-calibration, source finding, continuum subtraction, a bunch of different types of imaging. And some things do involve, all the beams, but most of it's done separately. So each of these little boxes can be, one or more, or maybe quite a few different Slurm jobs. And you're just throwing it all at the cluster. And so Matt, in the next talk, will talk about some of the different workflows that we use to process the ASCAP data, but I'll sort of just dig into a few of the little boxes just to give a sort of flavor of things that are happening. So some of the tasks, like here's the bandpass calibration, are what we call embarrassingly parallel. You basically just, each little MPI rank has a little subset of channels that it needs to process, and it doesn't care what any of the other ones do. But there are a few sort of pinch points, so they're all reading from the same place and they're all writing to the same place, right? So if you've got lots and lots and lots of processes doing that, you can potentially get congestion. So here, for instance, collaborator Richard Dodson from UWA, we were processing some simulated SKA mid data, and this had sort of 65,500 frequency channels. And Richard decided he would see how much he could push that, and he pushed it like all the way up to 65,500 MPI ranks. He got it down to, I don't know, 15 or 20 seconds or something to process the whole lot, which was good, but it showed up there were issues with our logging and stuff that only really showed up when you get up to thousands of parallel ranks. So that was useful. Best case. But most of the time when we're splitting in frequency, you need to combine the data. So in various different calibration and imaging contexts, you need to combine the data at some point. So we've got a nice setup where you can distribute across multiple nodes, and then we've got quite a flexible sort of merging setup that understands different types of grids and images and calibration matrices and things like that. And you can just put it all in this big merge, and depending on how you set things up, the merge knows, whether it needs to average across frequency or across beam or across Taylor term or whatever. So here, for instance, is the calibration that you might use in self-calibration, where you've got some sky model and say that's a set of images. And if the images have those different, moment map, the Taylor term split, then you can send the job of predicting the visit. So in calibration, you typically have two things, right? You want to simulate your visibilities, what you think they should be, and then you've got your actual data, and then you want to sort of optimize gains and leakages and things so that the two match. And so the most time-consuming part of that is generating your model visibilities, right? So we can split that up across a lot of different ranks, and then merge it all together. And so we've just got our estimate of what the visibility should be, and then we can, optimize, find the best solution. So there's a really nice way that that's set up in Yandersoft. And you can use pretty much the same sort of setup to do the imaging. So in imaging, you want to do something similar, right? You want to take an existing sky model. You want to do the same thing. You want to estimate what the visibilities are based on that model. But then when you've got them, rather than generating calibration equations, you can generate residual visibilities, and you can take those off to your parallel processes again, and this time you can grid them onto a grid, and you can Fourier transform them, and you can make a lot of different images with frequency and in different Taylor terms. And then you can merge them all together, now merging across frequency, and you can send that back to your clean process and do a sort of multi-threaded clean to update your sky model. Then you do it all again. And over here, this is just a plot of the times taken to do several of these sort of cycles around this full system, where you're going between distribution between lots of different parallel MPI ranks, and then you're merging all together into these sort of single spots where you're doing a sort of multi-threaded update of your sky model. Right, and just another example, I think this is the last example of the splitting. We can also, while we're splitting in frequency and Taylor term, we can also split over facets, which are little sort of chunks of the image, and that's quite useful when you start getting up into the sort of SKA scale images. So the larger sort of SKA images are it's going to be 100,000 pixels across or something like that. And a lot of the wide field techniques involve, going backwards and forwards between image domain and Fourier domain and image warps and things like that. And that becomes really prohibitive when you've got these really big images, right? So there's various efforts going on at places like Astron and other places to split the job up into some sort of fairly large facets and just get a better handle on the problem. So it's pretty easy to distribute in facets as well, and then the various mergers that happen, know what the facets are and know how to combine them in the right ways. Oh, sorry, there was one more. And we can also use pretty much the same setup, but rather than having equal facets, we can have our main field. And if we've got a bunch of strong sources around, we can put little facets around them, basically, and then process them really in just the same way with the same sort of mergers, but still do the joint deconvolution of all these fields at the same time. And that helps us subtract the side lobes from these strong sources from our main field, and it sort of keeps them out of the calibration process as well. And we can do the same thing with calibration. And we can so rather than doing a joint deconvolution, we can do a joint estimate of the gains in all these different directions and use that to sort of do a full direction dependent image-based self-calibration. And so this is currently in the ASCAP pipelines. So we haven't enabled the calibration yet because there's a chance you can overfit the problem here. So we're still working on doing that in a sort of a sensible way, but everything else is up and running. So this is just as an example, this is the same mosaic I showed before. So here, each beam's just been processed separately without worrying about offset images or anything like that. And you can see there's a really bright source in the middle, and it's cleaned okay in these inner beams where that source is inside the actual beam image. But if you go out a bit, then you can start to see side lobes from this strong source because the strong source isn't in the image for these beams. So follow this kind of process of doing the joint deconvolution, then we can clean those up quite nicely. And just to zoom in a bit, so one of the challenging beams for this particular processing job, if we zoom in there, so this is if you just this is part of the image. If you just make an image and ignore the offsets, you can see there's lots of side lobes. If I turn on the offset imaging, you can see it cleans them up, but it's not perfect. And the main reason for that is that in this particular job, we were only allowing the phases to be updated in the calibration process, but we're also fitting the gains. And if we turn on both gain and phase, if we let both the gains and phases change of the in the calibration process, turn on a bit of direction dependence. We can clean up the side lobes nicely. We also clean up the source down here a lot better. This source up here is still a little bit dodgy, and I think it's because there are some small pointing errors and they're sort of on opposite sides of the beam. And just to sort of confirm that, I put like a little facet around that and imaged again, and it cleans up quite nicely. But there's quite a lot of ways you can sort of attack a problem, or just by rearranging the distribution in different ways. Right. And finally, I'll just show another few updates that we've been doing recently. So I've shown that our processing is quite distributed, and the ASCAP observations are very distributed, right? We've got 36 beams on the sky. However, there are a few observational steps that are in their nature serial, right? And the main one here is the bandpass calibration. So what we do is we point at the primary flux calibrator, 1934. We need to integrate for a little while because we've got pretty fine resolution, and you don't have a huge amount of bandwidth per spectral channel. But if you spend 5 minutes on 36 beams, then that takes 3 hours, and you're eating up a lot of your time just doing bandpass calibration, and it really limits how flexibly you can schedule observations and how often you can move backwards and forwards between different types of observations. So our solution to that is we've selected several reference fields which have been chosen to not have any super bright sources or anything too complicated in them. And we can point our telescope at that instead of looking towards 1934. And each beam has its own slightly different little local sky model. And we can do our sort of calibration around the time of the observations towards that reference field instead of 1934, right? And so the idea here isn't to do a full new bandpass calibration. It's just to measure, a few things like changes in the delays, changes in sort of bulk amplitude scale factors. And then we can take a sort of a static 1934 bandpass that we did earlier, and we can just use this sort of reduced set of calibration parameter updates to update our bandpass and use that. And then every time we, update our beamformer weights and we form new weights on the sky, we can redo our calibration as well, and then reset our static bandpasses. So just an example of some of that. So on the side here, we're flicking through two things. So the sort of really ratty one with the big side lobes around the sources, that's if we use an old 1934 bandpass that's a week or so old. And the main thing that's happened in this week is that there's an on-dish calibration system that's used to keep the PAF beamformer weights nice and stable, but it can add delays and things across the beam, right? So that's what's causing this problem. Now, if we take delays by looking at a reference field and figure out how much the delays have changed, and we use those to fix up the bandpass, then you get this nicer image, but you can still see there's some sort of side lobes around the stronger sources. And that's due to the fact that when you look closely at what's happening in the reference updates, they're not pure delays, right? There are phase changes that are of higher order than the delays, right? So there's these small residuals, and there's a change. There are discontinuities at the beamformer edges because the on-dish calibrator thing happens in beamformer steps. But quite nicely, those changes are, I think I've got a thing here. The changes are really, really similar across beams. So here I show sort of 36 antennas, and in each plot, I've got 36 black lines that are all the change in the phase calibration update on the reference field for the 36 beams. And you can see they all lie right on top of each other. And they're mostly delay-like, right? So if I take away those delays and you just look, now you can see the sort of variation in the black lines more, but you'll see that any of these sharp features that are sort of offset are really pretty much spot on the same except for noise across every single beam. And so that means that we can use the sort of average change across all the beams to update the beams, and we can really knock down the signal to noise in our bandpass updates. So it's a little bit more complicated than we had hoped at the start, but we've got this way of getting around the fact that we have to use phases rather than delays directly. Right, I think this is my last slide, but this just shows here we're flicking through two things. So one, which shows some residuals, just sort of sponges around the brightest sources, is if you use just the layers, and the other is if you use like the average over the beams to correct the phases of the bandpass using the reference, the average phase of the reference. So that's working very nicely, and we've just turned that on, I think, this week, and hopefully it's making nice images. Sure there'll be some tweaks we need to make, but it's all looking very nice. I guess I'll end there.
Thank you, Mitchell. Are there any questions? Yes, in the middle, could you please go to one of the microphones?
I have two questions, if that's all right. Start with one, so we go. First one was, the way you described the identification of the bright sources that need to be dealt with and potentially special ways. You discussed it. I know you don't mean it this way necessarily, as if you didn't know that those bright sources were there in the first place, but of course, with practice, you know where all the bright sources are in the sky. So I'm just wondering if there are plans to fold in that information, not just as a starting sky model sort of generally, but also as a way to identify problematic sources and treat them uniquely from the beginning.
Yes, I should have mentioned that. We do use RACs. So yeah, so we use RACs in two ways at the moment. One is generally we use the sort of the in-field RAC sky model to do an initial phase calibration to lock onto the astrometry. But we also use RACs to pick bright sources around the field, and that's exactly what sets those sources that are given their own little mini facet to do a joint convolution on. I don't think that's it. Yes.
Can I have a second one?
Yes. Okay, thanks. Why do we?
Okay. So you mentioned the potential for pointing offsets, and I don't know if you mean antenna pointing, or if you mean that there's some variation in digital beams, but I guess I was wondering if it's possible at this stage to start pulling together information that you're getting from different pipeline runs on different fields and get a sense whether there are really just these bulk offsets of the beams that you could actually be solving as a a parameterized physical model rather than just random gains. Do you know what I mean by that? I'm talking about the way it was done with Western work and and those people about just literally doing antenna offsets.
Yes, there have been efforts to do that. I'm not entirely sure where they stand at the moment. I think one of the challenges is that a lot of the source finding and stuff that is done after the mosaics are made, so you lose some of that information that kind of comes out of that. Will come out from a single beam, but I mean we have there's a lot of potential to do stuff like that, particularly with the 36 beams, and so I mean I think we should do more of that. Yes.
Okay, thank you. So I think in a few time we will move on, and we can have a discussion with coffee break. So our next speaker is a colleague of Daniel, Matthew Whiting, also from CSIRO, and he will tell us more about the high performance processing software for ASCAP.
Excellent. Thank you very much. So it's good to follow Mitch. He's already given a bit of an introduction to what I'm going to cover. I'm not going to go into too much depth about the imaging. That's been sort of covered, but the sort of larger scale view of the overall processing workflows that we have. Does that? So yeah, so it's great to be here on Gadigal country. I'd like to acknowledge the traditional owners and pay my respects to their elders, past and present, and to acknowledge the Wadjuri Yamaji, as well as the traditional owners and native title holders of Inyurimana Ilgari Bundara, CSIRO's Murchison Radio Astronomy Observatory. where ASCAP is situated. So this is a view of a bit of ASCAP. Probably the key aspect, or sort of defining aspect, if you like, of ASCAP are these receivers, the phased array feed receivers at the prime focus here. So these are the things that give you the wide field of view. So we form 36 beams from the little elements, the 188 elements on the path. And those beams allow a field of view of about 30 square degrees on the sky. If you're familiar with the Southern Cross, it's about the size of that. Imagine a square with the cross sort of diagonal in it. That's the field of view that we get, which is quite big for a telescope of these frequencies and this style. It allows us to survey the sky quite rapidly, and this is really what ASCAP's geared around. Large scale surveys of the sky. We've got sort of 9 survey science projects that are underway in various stages at the moment, due to be finished all by 2030, and producing lots and lots of really great science. And my talk's about how we generate the products that allow that to happen. So the field of view, while it's great, comes at a cost. It produces a lot of data. It's basically lots of parallel streams of data, effectively 36 different interferometers running together. At full resolution, we get about 4 terabytes an hour coming from the site, the correlator on site, down to the Pawsey Supercomputing Centre in Perth. So that means a typical, say, Wallaby observation, which is the low redshift neutral hydrogen all sky survey that we're doing. They're 8-hour observations. That'll generate 32, 35 terabytes or so of raw data. And so that needs to be processed and handled and so on in time for the next lot to come down and so on. And this applies to all the different types of observations. You need to keep up with the observing. So this obviously was recognized very early on, and it was clear high performance computing, high performance data was going to be necessary to really deal with this rate of data and make the use of ASCAP sort of tractable. And this has gone into the software design. So Mitch has talked about ASCAPsoft and YanderSoft. So ASCAPsoft is sort of the largest suite of software that we use for the calibration imaging. The core calibration imaging tasks are all part of YanderSoft, which is sort of a subset of that. So that's the distinction there. And so we talked about sort of the parallelism that's been built in from the start into that code. A lot of MPI and OpenMP capability, but it goes beyond just the software as well. You need to consider what platform you're running on, ensure that you're able to handle the large amounts of processing that you're doing. So particularly good I/O. We're making lots of large files. You need to be able to ensure that they can be read and written and so on effectively. There's a lot of processing happening. You need that to be reliable. And you need to be able to manage all of this in a production environment. You need to be able to roll out new software changes. So it puts a lot of requirements on how you do that stuff. So the DevOps side of it and testing and so forth. So what we have in place for the processing is what we call the ASCAP pipelines. So this is these are sort of largely automated, well, almost entirely automated workflows that run at Pawsey, and are geared around taking the data from the raw visibilities that come out of the correlator into science-ready images, catalogs, calibrated data sets that get sent into the CASDA, so the CSIRO ASCAP Science Data Archive, and then released publicly after a short period of quality control. The pipelines themselves are founded on sort of bash scripts that manage the parameterization, manage the sort of the environment for the processing to run in. These create scripts, Slurm scripts that get submitted to the supercomputer queue, and then define the workflow. So each of these scripts are the things that run the heavy-duty applications that do the calibration, the imaging, the source finding, validation, all of these sort of things. The workflow is maintained through those Slurm dependencies. So you submit a whole bunch of jobs set up so that they execute in a particular way. You have streams of processing that end up with your final products, and I'll go through the thing later. Then layered on top of that are a whole bunch of tools and services and so on that really enable this to be run in an automated fashion. So things that recognize an observation has happened, copy the data from disk to disk to have it in the right place for processing. Those who were at Vanessa's talk yesterday would have seen all the different disks that we have, Ruby, Payne, and Scott. So moving those through, getting the processing running, moving it into the archive, and ensuring the raw data gets removed at the end to make room for more raw data, and the cycle continues again. We do get rid of most of the raw data that we take. We don't have the space to store all of that data. We really rely on the data reduction that goes into the imaging to be able to archive what we can. As it is, we've archived a lot. The CASDA is up to about 9 petabytes of data, almost all of which has come through these pipelines. For the actual survey science projects, that's about 5.5 petabytes. So it's a lot of data, a lot of large spectral cubes that dominate that size. Okay, so a sort of overview of the overall workflow. So Mitch talked about the different calibration schemes that we have. We have sort of no, that's not what I wanted. Sorry. Yeah, so we have the sort of the fundamental bandpass calibration that gives you the sort of the flux scale and so forth. And then the reference field calibration updates that we've just sort of recently introduced. All of this is setting up the calibration that you can then apply to a science field. When we take that, we process that sort of largely separately per beam for much of the workflow, making images of each beam and then bringing them together in mosaicing to form the image of the full field, and then running source finding and validation and so forth before it goes into CASDA. So relatively simple, you might think, but this box imaging contains multitudes. And this is where the complexity lies. We have a lot of different modes within the workflow to cater for the different science outputs and the different types of products that you want to generate to support the different science cases. So pretty fundamental and pretty much used by everything is the continuum imaging part of the pipeline. So this involves the self-calibration that we've already heard about, producing a continuum image or series of images, maybe Taylor term images, and continuum calibration tables that then get applied to the continuum of spectral line data sets. So the continuum data set can then be imaged, preserving the frequency sampling. So you get a continuum cube with, say, 1 megahertz resolution channels. Very good for polarization. We'll do that in full Stokes. We can do time resolved imaging so that you produce a series of continuum images at some cadence, and they get fed into a transit detection pipeline that was provided by the VAST team. So if you were at Tara Murphy's talk yesterday afternoon, you know about this. So they that then provides a series of candidates for transient sources and so forth. And then the spectral data down the bottom is kind of the really meaty one that produces a lot of very large spectral cubes with continuum subtraction and the Doppler correction and all this sort of stuff that has a lot of subtleties built into it. So we generally make a cube per beam and then mosaic them together. There are a couple of exceptions where we have modes where you just sort of stop the per beam processing at the there, the continuum subtraction stage, and then image all the beams together through a joint imaging process. And that is very good for the galactic H1, where you've got a lot of large scale diffuse stuff. And so doing it all together sort of preserves some of that structure. So we have a lot of monitoring and so on of how the things go. This is sort of a visualization of how the processing goes. This is as a function of time here. Each of these lines is an hour, I think. So this is for an EMU observation, so a 10-hour continuum observation. Each row here is a different beam, and the colors show the different types of jobs. It doesn't really matter what they are. They're basically the calibration and the imaging and self-cal and continuum cubes and so on. So you can see it's a 10-hour observation. This processing is taking about 5 hours or so. So yay, that's great. We can zoom out though. Following these, there are, of course, the mosaicing and the source finding, the validation. But the point here is that they only take a fraction of the resources in terms of the supercomputer than the bulk of this stuff does. And so you've got a lot of freed up resources here that you can use for the next field. We have 180 nodes on Photonics for dedicated for ASCAP operations. And so that's capacity to do a number of such fields. And it's this degree of capacity that allows us to keep up with the incoming data rate. And then you end up with something like this. I can't quite see whether this is coming through well enough, but this is an EMU image. This is of the southern galactic plane. The galactic plane goes along here. This is a bit of the sky. If you can visualize the Southern Cross and the pointers, it's kind of the opposite side of the pointers. Not that you'd know because it's radio, obviously. What you can see are huge numbers of blobs. I am an astronomer, I promise. So supernova remnants, H2 regions, and so on. And then out here, just lots and lots of background radio galaxies and so on. So you may think it's like jellyfish washed up on a beach, but it really demonstrates the quality of the imaging that we can get out of ASCAP. So it's not just compact point sources and things, but we're able to image really well the complexity of big, large scale extended structures. And you can see zoomed in here some of the exquisite detail that we can get with this stuff. And slightly gratuitously, sort of indications here of the field of view of comparable radio telescopes, I guess. So we get this instantaneously. This is everything from one observation. So this is So this is working quite well. And like I say, the ASCAP pipelines are running really successfully. They've been producing a lot of data for many years now, and we're at the stage now where it is really quite automated. A perk of my job is to look at these images as they come through, and just see bits of the universe that I haven't seen before. But often I don't get a chance to do that. The pipeline just continues on automatically, and particularly with the continuum stuff, it just churns through, and it's really, really, really effective. So I'm just going to finish with a few lessons learned and so on. I mean, it's been a long process of getting to this point of establishing these workflows on the supercomputer and really understanding how best to run them. There's been a lot of interaction with the PAWSI staff. That's been very, very important. And that's been one important lesson, work with the experts of the platform that you're using. But also test your stuff early at scale. There's always these pinch points when you move to a new level of either complexity in your data or complexity in the platform that you're using, and really understanding how that's going to affect what you think you're going to do. Your nice validation script that runs fine on your 5 GB cube won't work on a 2 TB one. I'll guarantee it. I mentioned file formats here. There's not too much to say there, but the measurement sets have been a an interesting experience because they do present challenges in terms of how you interact with them at scale and how they interact with the file systems on the supercomputer. They generate a lot of files. They're a sort of directory structure. Many files from many measurement sets can cause problems for your Lustre file system, and managing that has been an important part of getting to where we are. And I've got a thing there about containerization, and this is an interesting point at the moment. I can see Wasim smiling over there. Containers are held out really great hope in terms of having this sort of nice static configuration that you can just sort of deploy, and they generally work that way, but there are little gotchas occasionally, particularly around things that you need to know about the file, the platform that you're running on, particularly MPI, because the MPI enabled software inside the container needs to know about the MPI outside, and so you need to manage those sort of holes in your container and so on. So we've got an elegant way of doing this through layering of different things, and the SPAC tool works well with that. Our colleague Paulus Lahore, who works with us, is based in Melbourne, has done some great work in getting that sort of pretty reliable for our thing. But I think I will leave it there, and yeah, the ASCAP pipelines are working well and producing a lot of data, and looking forward to the science that's coming out of them. Thank you.
Thank you, Matthew. While the slide is still on here, you mentioned here containerization. On your earlier slides, I noticed that when you brought up the lines of code of the pipeline code, I presume there's the ratio of bash to Python is about 10:1 instead of 1:10. So why was that choice made?
Yeah. Well, okay. So there's two things there. So in terms of the actual ratio, so the bash scripts, you sort of have a lot of scripts aimed around the different elements of the workflow, and they're all about sort of creating really the Slurm scripts that are running. And so they run as bash scripts that you submit to the cluster and so on. Things, and then they run the applications and so on. The Python scripts are really around sort of more utility type functions and things that layer on that. Why we're working in bash? It works. It's something that sort of grew out. It kind of grew organically in some ways. We didn't sort of set out to design a big, here's the workflow up front and then start with that. It's kind of something that grew from the earlier days with beta and so on of starting to put together the workflow, because that's a very easy way to do it. And you sort of settle on a design for chaining your workflow together, and then increase that in complexity. And yeah, there's probably an overhead in maintenance and development a little bit, because it is, it doesn't have a lot of the benefits of a newer environment like Python, but it does work. Yeah. So we're exploring alternative frameworks, and there's been a fair bit of nice work recently, sort of alongside the core ASCAP work. So Tim Galvin and Alec Thompson have done some great stuff with Dask-based workflows. The trick, though, is you have something that's operational, it's in production. How much resources do you devote to replicating what you've got to get to the point where you are at the moment, versus maintaining that and continuing to develop that? And that's sort of been the trade-off there that you want. You stick with something that if you were starting afresh, you may not end up with, but you've got that, and so sort of bird in the hand is worth two in the bush type situation. Yeah.
All right. Thank you. Let's thank Matthew again. And then we continue with our next speaker, Wasni, who will be presenting on behalf of his colleague Himalan about GPU accelerated scan statistics.
Good afternoon, everyone. At the very outset, I'd like to warn you that it would be a challenge in a different front as well. I'm pushing technologies here. Unfortunately, my colleague Nimalan, who has done this work together with a few of us, could not make it to here, Sydney, despite the registration. The organizers have kindly allowed us to pre-record his talk and try and see how that works. So it's a pre-recorded talk, and I'll be here to coordinate it. So thanks, Andrew, and maybe just this.
Good afternoon. In this session, I'm going to talk about a GPU accelerated algorithm we developed for the ASCAP source data salary to reduce the time taken for continuous source finding. To begin with, let's take a look at the stats from the ASCAP continuous imaging pipeline. The green portions seen here are from imaging, and imaging is the most expensive step, which is expected. Flagging and calibration are small spots in the beginning. What's interesting here is that source finding is taking a considerable amount of time for the data that it is processing. A typical ASCAP continuous image is about 1 GB in space, and this takes 1 hour to process with 36 MPA workers and about 15 minutes to process with 121 MPA workers. The runtime and resource consumed, while not much in a single run, quickly adds up for large-scale surveys. We wanted to address this by investigating what was taking so much time, and we wanted to see if this can be optimized. So what is time consuming in Celery? Celery uses variable thresholding, a windowed statistics algorithm for pre-processing in which each pixel in the image has its own mean and noise threshold. In the 36 MPA worker scenario, variable thresholding was taking about 75% of the total runtime. This is expensive because of the large window sizes used, typically 101 plus 101 window. The choice of a large window size is to be able to handle complex sources in the image. For example, in the image shown here, a small window size like the bounding box of source A would not be able to calculate robust statistics when complex sources like B, C, and D are involved. Variable thresholding is indeed parallel in nature. Currently, after the migration to Cetonics, Celery is run with 121 MPA workers, and the runtime from 1 hour with 36 MPA workers takes 15 minutes. This switch between 36 MPA workers to 121 MPA workers was possible because of an upgrade in hardware. Cetonics having a larger number of cores per node and better interconnects made this possible. Now, an upgrade to hardware is typically expensive. The runtime has decreased, but the resource used by Celery has also increased. So the question still remains, can this be optimized and can resources be saved here? Looking at alternative approaches, Celery's predecessor Luchan used to calculate both the mean and noise map for the image in a single pass to the data. This approach can be carried forward to Celery. We also noticed that the usage of Casapo's masked arrays in sliding array math had cache locality problems. We explored MPA plus OpenMP instead of fully relying on MPA. The main advantage that we get from this is that later parts of Celery would have to deal with lesser message passing. The optimization to use MPA plus OpenMP and computing the stats in a single pass was looking promising. So we wanted to see if we could free up CPUs by introducing hardware acceleration with a GPU. The challenge with using GPUs here is that the window sizes used here are several times larger than the largest windows used in image processing. In image processing, the largest windows used are 11 cross 11, whereas here we have to deal with a 101 cross 101 window, which means that proven image processing algorithms cannot work here as they rely on the window being able to fit within the GPU's L1 cache. Without windows fitting within the L1 cache, time would mostly be spent fetching data and the memory throughput would be poor. These windows are also smaller than the threshold from which GPU sorting algorithms are issued. GPU sorting algorithms typically need millions of data points to be processed together, whereas we have 100,000 data points per window. This means that unless we process multiple windows together, there will be idle time and the occupancy of the GPU will drop. So we needed something to compute multiple windows simultaneously, maximizing occupancy, and also compute all the stats needed in a single pass to the data. So we came up with a new network model algorithm called as a scan statistic network to compute window statistics needed for variable thresholding. The image on the right is a scan statistic network for sliding window median. So what is a scan statistic network? If we start with a regular sorting network, which works well on GPUs, and remove a couple of stages from it, we get piecewise sorted data. This is due to the property of sorting networks. Another way to look at this property is that if we have all the windows from our image grouped together, they can be sorted together by removing certain stages from the sorting network, thereby achieving one of our goals of processing multiple windows simultaneously. Now, if we add additional kernels to the piecewise sorted data, we can get window statistics. If we average the central data points of each group and extract it, we have a sliding window median network. And this was the first step needed for Celebi's variable thresholding. The mean map is a sliding window median. If we now start to extend this network further with a transformation kernel to survive the median, a Bitonic merging network, and another averaging network, we can get the noise map needed for variable thresholding. In this way, all the stats needed can be computed in a single pass while working on multiple windows at the same time. This idea overall is quite generic, and with a different set of stages, we can compute a different set of statistics. For variable thresholding, we have other practical things to consider. For example, to account masked pixels in the image, we have to pad the data. We also wanted to try this on data-centric AMD Instinct GPUs. So during our implementation, at build time, we use the AMD toolkit to transfer the CUDA code to HIP and allowed the user to switch between NVIDIA and AMD GPUs when compiling Celebi. Coming to the results, this approach was 230 times faster than the baseline Cassio sliding MMR. Overall, the performance was bound by the memory throughput of the GPU, and GPUs with better memory technologies like HBM and its later generations perform better. What was interesting to see here is that consumer-grade GPUs with decent memory bandwidth can also be used in this approach, suggesting that this can be used for local analysis. Now, because we see a large improvement in this approach, we wanted to see if this can scale with the window size. And we managed to test this all the way up to 1024 plus 1024 window, something that is not possible to do with the regular CPU-based approach. Plugging this back into Celebi and using a configuration of 16 MPI workers and a single NVIDIA 800 GPU, we saw a 1.4x to 3x improvement in the overall runtime compared to the 36 MPI worker configuration, with an average runtime of about 20 minutes. Lesser CPUs used here means that the compute resources saved can be used for other parts of the pipeline or for other users in the cluster. This configuration is also small enough that that a workstation with a consumer-grade GPU could also be used to run Celebi. And for environments without GPUs, our initial approach with OpenMP is also a good alternative. So in conclusion, we talked about why Celebi's pre-processing was expensive, variable thresholding was taking a considerable amount of time, and this was because of its use of large window filters. The performance of pre-processing can be improved with parallelism, either through MPI workers, OpenMP threads, or through hardware acceleration. For accelerating this on a GPU, we came up with a novel algorithmic approach, scan statistic network, and showed that this approach can reduce the runtime as well as resource used by Celery. And finally, the idea of a scan statistic network is not restricted to Celery's variable thresholding and can be used in other situations where Windows statistics are needed. Thank you.
I can't promise to answer every question that you might have on this specific technical talk, but one thing before you ask questions, one thing that I'd like to emphasize was this work it emphasizes what things can be done when experts from different domains work together. So I'm not an expert on GPU, but when we describe our problem clearly to the domain expert, good things can come out. So if anything at all, I would like to give that message to this group, which is well known. And thank you, Andrew. It worked out really well. Thanks to the AV team. Any questions, please?
Any questions? Yes, please. Come to the microphone.
Thank you, et al. And friends. I very naively, and I don't mean this the way it sounds, but I would have expected more of a speed up going from the CPU to the GPU implementation. I can pause there if you wanted to say something.
No. I think what your statement is very general, true, but I think as Nimalan also highlighted, the specific kind of problems that we're addressing to solve here, like the window sizes, for example, is enormously humongous compared to what normally one would use in image processing on a GPU. So, yes.
Entirely fair. In the same breath, I wanted to ask, I mean, that's your GPU side code and the complications there. What type of software or how are you getting data onto the GPU and therefore off it? Are you using any like Python-based pipeline? What's the process there?
Are you saying how did we interface it? I think
yes.
I think the code is compiled. How should I say this?
Is it all like native C?
It's C++. Yes, if that is what you're asking, it's
Yeah.
native C++. Yes.
Okay. I mean, again, you don't have to answer now. I can bug you later.
Absolutely. Plus, like I said, the technicalities of it, I might not be able to answer given my domain expertise is not on GPUs. But I promise I'll get back to you after having talked to Dr. Nimalan on any specific questions that you might have. But that question particularly, yes, it's wholly compiled in C++, and yeah.
Again, I mainly ask because I feel like at some stage we probably faced a similar issue where we weren't seeing the speed up we wanted, and then we actually fiddle with things on the host side to make sure we kept the GPU busy enough all the time.
All I can say is there's so much more to discuss together on this. So glad that you came up with the questions. Let's chat offline and see how we can collaborate on this, on your specific problems.
Thank you. Are there any further questions to Wasim? If not, then thank you, Wasim, for helping out with the questions.
Thank you.
And then our next speaker is our co-chair for today, Max Rokov, who is going to talk about large-scale calculation by tracking Mesa observations.
Thanks, Stefan. And yeah, we'll change to compact array. And I'll use this opportunity to acknowledge Gomeroi people, traditional owners of the observatory site, and pay my respects to the elders past and present. And I must say that this talk will probably be quite boring because it doesn't have AI, it doesn't have wide field, it doesn't have wideband, and all my sources are point sources. So basically it just shows some of, and yeah, at the end also, I don't even plan to do this kind of thing. So this project started when we were building ASC app and commissioned it, and I kind of wanted to have it as simple as possible. But as usual, nature doesn't cooperate, so quite often we have to dive into study of the instrument, even if we don't plan to do it. So as I said, so this thing came up out of my science field, and for science, I'm studying masers. So masers are cosmic sources, which are, well, sort of similar to lasers, but in radio. So as you know, like if we have any quantum system, like a molecule, so we get 3 types of transitions. We get spontaneous emission, where molecule goes from level with high energy to low energy and emits photon. We can have absorption, where photon is absorbed, and of course the molecule goes to higher level, or we can get stimulated emission. If there is a photon at the correct frequency, then the second identical photon is emitted. So basically, in normal conditions, all these processes are balanced, and you get essentially a normal situation with black body kind of output if you have like equilibrium. However, if you put some process which we call pumping, which you cannot do in 2-level system, you need some other levels, and somehow you end up in a situation where more molecules are at the higher level, then you can get amplification instead of absorption. That's what's called masers. But for the purpose of this talk, you can think of masers as just a spectral line, which is usually like stronger than thermal spectral line you would expect from the same source. So typically, like these kind of sources, well, the sources I'm studying are usually appearing in regions of high mass star formation. And here you can see the example of a field. And by the way, like all images, spectra I show will be for the source it's all about. So all these different spots are different kind of masers, which are different transitions or different velocity components of the same transition. And they're not necessarily at the same place. They all don't share the same properties. They can come at different varieties. And in particular, in my talk, I will concentrate on 2 masers. So one of them is 9.9 gigahertz methanol maser, and it's located where that line shows. And the other one is 6.7 gigahertz methanol masers, which is not located at the same place, but seen in projection to the same H2 region. So you can see that some spectra are extremely simple. It's essentially a very good Gaussian line, and it happened to be extremely stable. And by the way, if you do like accurate fitting of the profile, you can get the velocity down to centimeter per second level. And that took me maybe like a few years to get down to that level, because of course it discovered a lot of bugs in the software. But again, that's usual. And in some other cases, you can get a much more complicated spectra, and moreover, it can be variable. So here you can see the spectrum of 6.7 gigahertz maser in the same source, and one component in particular shows periodic variability. So this periodically variable 6.7 gigahertz masers was sort of a new thing in early 2000s when this project was first conceived. In principle, up to today, we don't understand those kind of periodic masers very well. So there are plenty of theories. Back then, in the time when this project was started, I was joking that there are more theories than sources known. Now about 30 periodic masers known. Typically, it's a feature of 6.7 or like other class 2 different classes are kind of different pumping of these masers. But in some other species like OAH, they're also found. So periods go from like a month, or 20 days, I think is the shortest, to just over a year and a half or something like that. And we try to understand whether the main motivation of the project was to understand whether the variability is because the pumping changes, the physical conditions change, or because the background radiation, which these masers amplify, changes, because different theories basically predict different things. So that's why these 2 transitions were chosen, 6.7, 9.9, because their pumping is antagonistic. If you have one amplifying, the other one would go down. And compact array was the only instrument which actually allowed us to observe these 2 transitions simultaneously. So, as you guessed, compact array was used as the instrument to observe this. It's not very common to do monitoring observations with an interferometer, and that caused us to at least think about it a little bit more. So we did about one epoch every 20 days, and regular observations continued for more than 7 years. I've done like a few sporadic epochs after that, but at least it wasn't as part of the original program. We used CAB. That's our previous correlator. Well, it's definitely previous because it was shut down earlier this week. If you haven't seen Chris's talk earlier on about our new correlator, well, it's too late now, but you can ask us during the coffee break what it's all about. So as I mentioned, we could observe 6.7 and 9.9 gigahertz simultaneously because receivers had 8 gigahertz bandwidth, still have, and with CAB we could digitize 4 gigahertz out of this 8 and put it everywhere, basically within that 8 gigahertz. And typically we observe just in 3 scans of 15 minutes with appropriate calibrations and so on. So care was definitely exercised to put the get the good data set, don't observe in shocking weather and things like that. But of course, things are never perfect, especially at our side. And here we come to like how we measure it with an interferometer. So observations are short, so imaging is out of question here. And yeah, if we consider how we measure fluxes from the imaging, it's another kettle of fish. But for short observations, we basically have to do non-imaging analysis. So if we have point sources, and masers are good point sources for compact array, then, well, at least visibility is should be represented very, wrong one, should be represented very easily with this equation. The simplest way to get, like, if we know that the source is in the phase center, can put it there with appropriate shift and everything is perfectly calibrated, then technically the flux would be just the weighted average. And technically that's the only way to take weighting absolutely correctly. And it's actually kind of subtle thing, but important. So when if we try to do like use any other methods, then it may be very non-trivial to take into account that all antennas are slightly different. Well, in theory, they're the same, but in practice, they're slightly different and it may be important. The other option is to do just least square fit for this model into our visibilities. It might be a bit more robust to some subtle errors. Another option, do a phase-only self-calibration and repeat one of these 2 steps. We can use closure products, well, triple products. So essentially, it's just a product of 3 visibilities if we go across the triangle and just essentially do some kind of average across all triangles. So the amplitude of it will be our flux, and it will be very robust against phase errors. And finally, we can try to use amplitudes after appropriate debiasing, and I will say a few words about it later on. So even we have multiple ways of getting the flux, it's always nice to compare them because the result may surprise you. I want to show one interesting example where I get a difference in fluxes predicted by different methods, and the data look absolutely normal, actually. So I didn't know why one give me one way of getting the flux give me higher flux than the others. And then I looked at observing log and realized that there was so-called midweek RFI, which is airborne radar. So it was sufficiently far away and didn't cause any like visible problems in the data, but somehow comparing these 2 methods picked it up. There were plenty of other things when like fine-tuning calibration, getting the right parameters and things like that. So yeah, all these cross-checks are extremely important. So beyond comparing different methods, we compare fluxes, say calibrator fluxes for each scan. And again, results may surprise. Compare noise estimates, where you process the data by dropping one antenna in turn. So when everything is automated and scripted, it's possible to do this kind of thing. In addition to this, my calibrator loop included the test calibrator, test source. So it's essentially yet another calibrator. So we can deduce flux for it, treating it as a calibrator or as a source, and compare results. So the first results show the very interesting feature like dropouts like that at 9 gigahertz and 6 gigahertz. Well, sometimes had a hint, but often not. And with improving calibration, I could kind of reduce the depth of these dips, but I didn't know whether they were real or not, because again, based on the data, I should have believed them. And playing with it, or largely dropping one antenna in turn, I realized that actually the values change quite significantly when you do that. And then I realized that basically the problem was with the flux scale calibration, which we do on our primary calibrator 1934-638, rather than the data themselves. So the flux scale calibration in the standard compact array data reduction is done like with TaskMF boot or GP boot. They have very similar algorithm, which actually uses triple products. And that's why I always thought that it should be robust to any phasing problem. However, it actually relies on the fact that all baselines or antennas, I should say, should be already cross-calibrated between each other. And when the phase stability is not ideal, and by the way, I never observed in the shocking weather here, so there was no observation through thunderstorms or anything like that, and it's also a centimeter wavelength observation. And I definitely seen people observing in millimeter in the weather worse than here. So it uses triple products, but if the individual antennas are not cross-calibrated, you can get a bit of a bias. So naive approach to solve this was to essentially extend the same fit, but to solve one factor per antenna. So it did work, but give me a bit of a bias. And in the hindsight, yeah, by the way, this first part, we had the old CX receivers, which were a bit more noisy, and plus 9.9 gigahertz was a bit out of the band. So it's not surprising that we had high noise here, but bias was something I wanted to get rid of. And the interpretation of this result is that my primary calibrator scan had good enough signal to noise when we tried to deduce single factor, but when I tried to deduce one factor per antenna, that was a little bit too much for the signal to noise I had in this data set. So I initially tried to understand statistics of triple products, which gets very non-trivial when you get down to like low signal to noise. And then I realized that I basically try to predict it as the product of 3 amplitudes, and I probably should just move to amplitudes instead. And that's what I did. So much simpler equation when you have some kind of amplitude estimate through debiasing process, which for like amplitude, if we assume that amplitude is Ricean distribution, we can use one of the debiasing procedures. It's actually happened to be an interesting topic in math in general, trying to do this kind of debiasing, especially in low signal to noise, but this simple inversion technique seems to work fine. So everything depends on this R-square statistics, which is just the ratio of the first raw moment to the central second moment. And basically when we get that from our data, we just solve this equation. It looks scary, but because those modified Bessel functions, they are easy to differentiate. So it's actually very easy to solve numerically. It converges very quickly in like less than 10 iterations usually. And once you solve it, theta is essentially a signal to noise. So it's the ratio of flux to noise of the underlying Gaussian process to that Ricean distribution. And then once you know signal to noise, you can get, of course, should be sigma squared here. You can get the actual noise, and you can get the flux. And by the way, you would have to drop the baseline if that R-square happened to be below this critical value, because it's not possible in Ricean distribution, but in practice it can of course happen. So anyway, that worked reasonably well. And while we're on this page, I can tell you that you can actually take it even further and use the fact that you actually get the estimate of noise and flux for each baseline and use the same math to estimate the flux of the source based on the data. So the only devil in the detail here is that you have to weigh the individual baselines appropriately, and when all antennas are not quite the same, things may be a bit non-trivial. Anyway, it worked and gave me a bit less bias at the end. And you could see that this 9.9 gigahertz happened to be very predictable. So it has a nice trend, losing like about 160 microjanskis every day. And it continues, well, for these 7 years and probably for 5 years after that, at least. So after I take this trend out, so I get this kind of thing, which is definitely much more noise-like, but you can start to see some periodicity here. One interesting problem is that this period is about 1 year, which of course tells us that it's probably not our source, but something else. It took me a while to dig into this, and eventually I found an interesting dependence that if I plot that sort of residual flux relative or absolute with respect to difference between elevations of my secondary and primary calibrator, I get this kind of dependence. So not great. So basically we have some gain elevation effect, which is not corrected. And traditionally we ignore gain elevation effect for compact array data reduction simply because we always have like a calibrator observed close to the source. And somehow we haven't thought, well, at least in centimeter wavelength and millimeter wavelength, all millimeter astronomers, which virtually non-existent now in Australia, but at least they knew the recommendation to always observe primary calibrate at the same elevation as your secondary for that good reason, because beam at like 3 millimeter is changing all the time for compact array. At centimeter, no one bothered with this kind of thing, and yeah, we had to correct it. So apparently the code of Myriad even like used to have that gain. Myriad, by the way, the software which we often use to process compact array data. So it had the gain, the old gain curve from early 2000s. And moreover, initially it was not even possible to use with new receivers because of the frequencies. It was just outside the like if statement in the code. So by the way, I lost track how many times I had to look in the code just to see what exactly it is doing. So after it was enabled, yes, like I could see that gain correction improves things. And moreover, I remeasured the gain curve, got some very strange results because I got entirely different curve to what we had earlier, which is maybe not surprising because we have different receivers, different feed horns and so on. Now, but what was surprising was that antenna 4 happened to be different from the rest 5 antennas. Not sure why, not hugely, but significantly. And moreover, it didn't solve, like, well, it flattened this curve, but it didn't remove all annual periodicity, just removed extreme outliers. So the mystery is still remaining. And by the way, I show just the final results I had. So this is my best time series I have. I didn't find any periodicity in this maser. Well, it's nice to know that it's dimming. And this is the latest residual I have. So the points I want to make is obviously monitoring observations done in a very systematic way with systematic processing by scripts have very good potential revealing some weird systematic artifacts of our system. And it's great that we actually had a source which acts in a very predictable way. If it was varying like crazy, we wouldn't be able to get down to these low levels. And standard methods of data reduction give you at least a few percent. So if you're not interested in absolute calibration better than few percent, then you don't need all this stuff. And be careful about the weather. Even in centimeter, it may bite you. And moreover, what puzzled me is that at 6 gigahertz, simultaneous observations at 6 gigahertz, I had much better data than at high end of the band. Same simultaneous observation. Thank you.
Thank you, Martin. Are there any questions? So I have one. So you showed that there is a flux difference between the calibrated and target, and there's elevation difference. Is it known why that effect is there? Is that due to gravitational deformation, air mass differences?
Well, just gain elevation effect of some sort, probably gravitational deformation, then subreflect. I think one story I've heard, I'm not 100% sure whether it actually backs up by anything, that the subreflector, well, it's supposed to slide under gravity when we actually move. And when the array was built, the bolts were not tightened to the right tension. So it basically doesn't move the way how it's supposed to. However, by the time it was discovered, lots of photogrammetry and other things were done. So basically no one wanted to change it back, basically, because it potentially means that we had to redo this. So it is one possibility. Second, just no one cared, honestly. So I expected that, I didn't even like that kind of accuracy is not required for my work. I just want the number and say like everything below that is not believable. I'm already convinced that there is no periodicity in the source. So yeah, it's supposed to be an easy project, but because I could see some systematics in the data, I had to dig further.
Thanks. Any other questions? If not, then let's thank Max again. And move on to our final speaker for this part of the session, John Chu from Harriet-Watt University, who is going to tell us about compressive imaging using rank 1 projections.
Great, the green button is next. So good afternoon, everyone. I'm Chung Chu, or you can call me Taylor Chu as well. My supervisor is Eve Whale at Harriet-Watt University in Edinburgh, Scotland. And this work is in collaboration with Olivier Leblanc and Laurent Jacques from UV Leuven in Belgium. And I swear I'm not competing for the longest title, but it's a modulated rank 1 projection and overall data dimensionality reduction scheme for imaging in radio astronomy. So I'll first talk about quickly the challenge in data storage, which most of you already know. So if we have a data model y equals phi x hat plus n, where x hat is the image we want to seek, we have the data model phi, which is the ungrading matrix that would form the data y with some complex Gaussian noise n. The data y, the data volume is VB, where V is the number of baseline. But we can also view the data as a covariance matrix cube, which is size Q by B. So VB is just the upper triangular part of all the covariance matrices you see in the blue cube. And as you all know, with SK and all the other next generation telescope, we're going to end up with a very large amount of data. So this is a scheme that we aim to compress the data such that we don't lose any quality in the imaging quality. And MROP can be basically summarized in a nutshell in this illustration and equation here. So with the blue cube, we have the covariance matrix at each snapshot, and we want to project it onto a rank 1 matrix, which is the product of the red cubes you see here, the alpha and beta. The product of alpha and beta, the alpha and conjugate transpose of beta is a rank 1 matrix. And you can form the vector alpha and beta by selecting some Gaussian complex random variables or unitary vector. And then we also have a black and white vector in the back we call gamma, which is just random Bernoulli variable. So we first project the covariance matrix at each snapshot to the rank 1 matrix, and then we apply modulation. And this process can also be summarized by the tensor product equation you see in the blue box. Sorry. I forgot to mention the number of projections can be chosen and is capital P, and the number of modulations is capital M here. So at the end, we end up with data size capital P by capital M. And during imaging, using this MROP is basically just appending the dimensionality reduction operator to the data model file, which is just appending, which is just doing the rank 1 projection followed up by the modulation, which then form the phi prime you see on the left. Hopefully it will be smaller than R or phi, and we'll see if that is true or not. And to dive a little bit deeper into how it works, the classical data acquisition, which is not compressing any data, acquiring data in the traditional way, we have the voltages fixed at different time, and then we do cross correlation to get the covariance matrix at each snapshot, and then we take the upper triangular parts and apply some feasibility weighting. And if we accumulate these feasibilities over however many snapshots we collect, then we end up with the feasibilities that's scaled with Q squared B, which are used in imaging. And in MROP, we start with the same process, but after feasibility weighting, then we apply the rank 1 projection to the covariance matrices at each snapshot, followed by the random Bernoulli modulation that I mentioned earlier. And we sum over the product of this process for all snapshots, so that we end up with the MROP vector of size capital P by capital M. And you might notice that we call that feasibility-based MROP here, because we've also proven theoretically that it should also work instead of on the feasibility, it should also work on the voltages acquired from the antenna directly. And we've proven that the rank 1 projection, when applied to the voltages, is actually equivalent to random beamforming. And after that, we can just apply the random Bernoulli modulations the same way and accumulate over the snapshots and end up with a vector of MROP and never forming the feasibilities. And to validate our compression method, we simulated observations using VLA and meerkats. We formed 100 images from the 4 images you see at the bottom, and we exponentiated them into dynamic range intervals of 10 to the 3 to 10 to the 4 and 10 to the 4 to 10 to the 5 to see how it performed at different dynamic range. And these images are all 256 by 256 pixels. And for imaging, we're using a optimization algorithm called URSI, which stands for Unconstrained Sparsity Averaging Reweighting Analysis. It's a pure optimization-based algorithm that exploit the sparsity in 8 different wavelet domain and also the basis domain. And for the observation model, we're only considering uniform weighting with a super resolution factor of 1.5, which is the scale in the Fourier grid. So I'm going to show you some plots here. On the left, we have the asset now, and on the right, because we're trying to see how well the method performs in high dynamic range cases, we also compute the SNL in the logarithmic scale of the reconstructed images. And in the red, all the lines and the points represent the average values. The shaded regions represent the standard deviations. And in red, we have the classical or the uncompressed case. In green, we have baseline dependent averaging. And in blue, we have our method MROP. In purple, we have CROP, which stands for concatenated rank 1 projection, which is simply a variance of MROP without modulation. And in orange, we have what we call subsampled, which is a naive way to randomly select part of the covariance matrices at some snapshots so that we end up with similar data size as MROP. And you can see for both MROP and CROP, if we compress the data to at some points, we will end up with the same imaging quality as classical and BDA. And more particularly for MROP, if you look at the x-axis of both graphs, we have D over N, where D is the data size after compression, and N is the image size, the number of pixels. And for MROP, it's actually around D to N ratio of 1. So somehow the compressed data size, when it's equal to the image size, we get equivalent or similar performance as the uncompressed data or BDA. But for CROP, because there's no modulation, we needed more projections. So the data size is actually larger to get the same performance. And for subsampled, it never reaches the same performance as the other methods, which is expected. And then again, for MROP, if we go below image size, we start to see degradation in the performance. And just for validation, here the plots for the higher dynamic range interval for VLA, the low dynamic range interval for Meerkat, and the high dynamic range interval for Meerkat as well. And for all 4 cases, we can have the same conclusions that at around compression to image size, MROP can perform similarly to classical scheme or BDA. And a drawback with MROP is that you can see on the left and right hand side the average time per iteration of the URSI algorithm. The red line, if we use that as a baseline, the green line BDA, obviously we're going to have faster per iteration time. But for MROP, because we're appending more operations on top of the grading operator, we end up with longer per iteration time. But in this simulation, we never exceed twice the time of the classical scheme. And to show the validation results in visually, this is an image of ACO 2034 or ABEL 2034, simulated with VLA with dynamic range around 10 to the 5, so which is around the highest dynamic range that we've tested. And on the left, we have the ground truth image. On the right, we have the dirty image of the classical scheme. And I'm going to flip between reconstruction and ground truth images, so you could compare. So this is the reconstruction with the uncompressed data from the classical scheme. You can see almost everything is well reconstructed, just some leftover artifacts that is more related to the reconstruction algorithm. And in the residual, we have recovered almost all the sources that are significant. And then for BDA, again, the performance is very well, it's matching classical scheme. Also in SNR and log SNR is comparable to the classical scheme as well. And now for MROP, for this particular compression ratio, where we compress the data to the image size, which is equal to 7% of the original data size, we also get comparable imaging quality in terms of both visual inspection and the SNR and log SNR metrics. But if we compress further with MROP, we start to see some drop in SNR and log SNR. You might not notice too much visually, but if I flip back and forth, you will start to see some of the phase emission is not being reconstructed anymore. And then in the extreme case, if I compress the data to 0.4% of the original image data size, then again we lose the phase emission. And this might seem impressive here, but I think we picked a lucky image here, because from the graph you could see the drop in SNR and log SNR is much higher when we compress further. And you might ask me, it works well in validation, but does it work well in real data? We have proven that it actually does, and you can be the judge of that. And before that, for in real observation, we have to deal with flagging. And in the classical scheme, we simply just discard the flag data. But in MROP, we just need to set the terms corresponding to the flag data to 0 so that they don't contribute in the projection. And so for real data, we have the quasar 3C273 observed by BLA. This is still using the URSI algorithm with a uniform weighting. And on the left, we have the dirty image by the classical scheme. In the middle, we have the reconstruction. And on the right, we have the residual dirty image. And in the reconstruction, we have two zoomed in spots. The yellow one is of the center of the quasar, and the red one is the end of the jet. And then the next slide, I have the reconstruction of MROP. And if I flip back and forth, you see that the reconstruction visually is very similar. And also the residual is very comparable as well. But the compression here is compressed to the image size, which corresponds to 9% of the original data size. And sorry, I forgot to point out that the residual dirty image here I show is using the classical measurement operator so that we can compare the residual directly with the classical scheme. And in this slide, I also show the residual computed with the MROP measurement operator to show that it fits well to its data in the algorithm. And so to summarize, MROP offers a new way to compress data in radio interferometry without sacrificing imaging quality. And this is, the work has been submitted for 2 papers. The first paper was written by Olivier, which focused on the theories and the foundation. And the second paper, which is based on, which this presentation is based on, focus on the application and the validation. And after these 2 papers and the presentation, we're going to focus on wideband imaging and trying to handle calibration with MROP. And also, as I discussed earlier, the per iteration time of MROP is slower than the classical BDA schemes. So we would want to investigate if there's a way to accelerate this compression method so we don't lose performance in computational cost. And we have our FastLib, which is a code of libraries with algorithms developed by our groups. If you're interested, you can go onto this link, and there's my email if you have any questions or if you want to collaborate. Thank you.
Thank you, Taylor. Are there any questions? Yes, question.
Yeah, I'm a bit confused here. When we talk about dynamic range, do you talk about reconstruction dynamic range or compression and the visibility?
Sorry, the reconstruction dynamic range, the peak of the image to the noise of the image.
I have also a question myself. When you so you start with visibility tensor, which you then apply a number of projection operations. So one operation is projection operator is in the space domain, like you mentioned, can be done in beamforming. But the other operators, they are then in the time or frequency domain, I assume.
It's in the time domain.
And so how would that work if your data is time varying? You already mentioned that it needs to be extended by calibration, but one of the things we calibrate for are time varying effects.
So the disadvantage I mentioned earlier is that we append the modulation and projection operator to the measurement operator or the gridding or ungridding operator, because we always go back to this ungridding and gridding product, so we can always handle calibration with this gridding and ungridding operator there.
So in that operator, you basically go back to the visibility tensor.
Yeah. But that's also the curse of this compression scheme, which makes it slower.
Okay. Any further questions? If not, then we can break profit. Thank you all for coming.